Then you have to also dimension suitable pipe size for you and calculate what are the total losses of your system and total efficiency of the system. And I have also given contents of the report for you. It should follow these topics: description of the system, pressure level and oil type selection, cylinder dimensioning, pump dimensioning, other component selection, pipe and tank dimensioning, losses and efficiency, and electric motor selection. And here this electric motor selection means only that you have to calculate how much power you need from electric motor. So I don't accept that you would select some ABB motor or something like that. No, this is not the case, but you just need to calculate that how much power would you need to rotate this hydraulic pump. And these contents, I think it is in such order that it makes sense that you can create your design in the same order, mainly in same order. Okay, any questions at the moment?
No, not really.
Yes. Okay, so next thing I think could be that you will select the groups. I can see that there is still only 10 people in this meeting, so it means that not all students are here, but still you can start thinking about these groups. And now this letter here tells what are your initial values. So there are groups A1, A2, A3. They have the same initial values, and B1, B2, B3, they have also same values and so on. So you should create these two people teams now, and if there is a good reason, it is possible that we can create also three people teams. But if you are going to have this three people team, then it means that also I will have a little bit more strict evaluation for this three people team compared to two people team. By the way, do you see this text as ryhmä or do you see it so that it says group?
Yeah, we see it as a ryhmä even if the language is selected with English.
Okay.
Well, but I don't think it's a big deal for us.
Yeah. Okay, now I see that already 7 people have selected the group, which is the majority of the people what we have here at the moment. And I think that we can go on. And I told you that the main thing is to find out, or thing what you should start is to find out this correct cylinder forces for this kind of scissor mechanism. And I told you that you could use SolidWorks to find out the mechanism and the correct dimensions and angles and such. And now I think it is the time that I will show how it could be done. So I will open SolidWorks. You could do the same. Okay, it didn't open. What is the problem? Okay, so if we just open a new part, maybe I will put this record on so few people hear that maybe they need to see this also later. So sketch is everything what we need, and no matter what is the plane. And then we need to start creating this scissor. My aim is to put the scissor in the middle. So I will select midpoint and origin and say that they are coincident, and the same for this other cursor. Okay, so now they can still move like this, but the middle point is in the middle. Then I can say that these are equal length because it's a symmetric scissor lift. So I select the both lines and say that there is a relation that they are equal. Then I think that it makes sense to give a length. This is something that we might need to change later, but I will now put there, for example, 1200 millimeters. Then next thing that I could add here is that this endpoint and the other endpoint are horizontal. And now it already moves like I want. Or do you agree?
Yes, I agree.
Okay. Then I could give one dimension from this point to this point, which shows that what is the lifting height. And instead of this some number, I could say that this is a driven, so that it is only informative. It's not locking the system. And I could say here that in addition to this dimension, it would be visible this lifting height like this. And now this number is changing depending what is the position of the lift. So if we go back to Moodle and see this assignment, there were these initial values, so that the lifting range should be something between 0.1 to 1 meter or 0.2 to 1.1 meter. So at the moment, I'm in such level that I'm able to fulfill those requirements. And then the next step is to put the hydraulic cylinder there. And the simplest way to show the hydraulic cylinder is simple. Draw a line like this. And now this will illustrate our hydraulic cylinder.
Should we somehow calculate the best position for the cylinder?
Yes, I think later on you need to do some calculation to find out the suitable position for it. But at the moment I just want to put here this dimension, and also here I will tell that the cylinder total length and it is also a driven. And you see that if we want to lift, for example, from 0.2, now the cylinder is 82 millimeter, and if we want to lift it to more than 1 meter, it's 199. Well, we see that how the cylinder length is changing, and we would be able to find out what kind of stroke is needed, and if such cylinder is really, if we are able to find out the correct cylinder, to say so. And we need to play with this information that what is the cylinder position, how it is fastened here, what is the distance. I think we need to have a much longer cylinder in real life. So I think that this distance needs to be much less compared to what it is now. So I will put, for instance, 100 millimeter here. And in a similar way, we can give information that what is the distance from middle joint. And now if we want, we can also change this so that it is not driven, but it is some exact value. So we are able to put here this, for example, 200 millimeters and see what is the cylinder total length in this case. And then this 1100 millimeters and see what is the cylinder length in this case. And now the difference between the cylinder total length here compared to cylinder total length in the minimum position, then we get the information that what would be the stroke, suitable stroke for the cylinder. And this is some kind of iteration. You need to find out what is the suitable position for the cylinder, and it affects also in the amount of force what we need to take out of the cylinder. It's not only the stroke, but I think you will understand it quite well that the more or it depends on the position of the cylinder. If it's in a very horizontal position, then we need much more force, because in real life it's only the Y component what is used to lift this scissor, and the X component there is no real use for it.
Is it, well, the X component is eliminated by friction, static friction of like scissor legs?
I think we don't need to take care about this friction in this problem at all.
Okay, just for curiosity.
Yeah.
But
so in real life, of course, the friction has some influence, but I think the friction is still so small compared to the forces what we get here from the cylinder that it doesn't play very important role. So were you able to follow and create your own mechanism?
Yes, we can.
And as you can see, if I change the cylinder attachment point here, of course the cylinder length is changing all the time. All right. And what do you think, what is the position of the scissor lift where you need the biggest force out of the cylinder? Is it the starting point or somewhere else?
I'd say starting point, maybe, because in starting point the legs are quite horizontal and therefore their Y component might be quite excessive.
Yes, yes. you're absolutely right. So the starting point is the point where we need the biggest force, and the cylinder force should be calculated in this position. Now it depends on the initial value. That is it this 100 or is it 200? And do you have a clear idea how to do this calculation now? If we would imagine that this would be our starting position, how would you define the cylinder force from this point?
Well, we have x forces acting, well, forces in y direction, sorry, from the load. Then we have reaction forces at legs, right? As they call so. And they have also some kind of y component and x component. X components should be eliminated by each other. Mm-hmm. And then y components are also compensated by the not compensated by x together with the y component of the cylinder, and y component of the load should be equal to the sum of the reaction forces at legs and y component of the cylinder. I guess that's it.
So how I think you should start, if I will still try to clarify it more. If we have a look at this scissor lift and the external forces what we have in this scissor lift, am I able to draw somehow here? How does the zoom work? Annotate and draw. Let's try. So we have one force acting here. We have another force acting here. And this is the load, right? That comes from a car. And then we have a support force and another support force. They should be now directly pointing down. I'm sorry if they are not looking like that. And if the scissor lift has this kind of system that there is an okay, come on. Well, it has an two sides and only half of the load is in one side. If the total load is called F, and if the one cylinder is taking care of half of the load, we still can split the load, this one half of the load in two, if we think that the load is symmetric. So we would be able to say that we have this F divided by 4 here, and we would have F divided by 4 here. And then we would have some support here, let's say A, and let's say B. And if we have a fully symmetric situation, all of these components are equal. Do you agree?
Can you repeat your question, please?
So if we have a fully symmetric system, do you agree that all these components, this A and B and this F divided by 4 are equal? If we just look at the external forces of this scissor lift.
Yes.
Yes.
Yes. And then if we only consider this one scissor, let's clear the things here, and am I able to hide some of the lines? Or is it just hiding the whole sketch? Okay, it hides the whole sketch. Okay, I will draw just. What happened? Okay, it is still there. It's just. Let's create a new sketch. And we have this one scissor here. And then we have 2 points here, one which is in the middle. And then we have this cylinder attachment point somewhere here. And now what happens in this one scissor is that we have this. Oh, sorry. We have this external forces, but in addition to that, we have this internal forces, the cylinder, and a counter force here. And now you have you can based on this free body diagram, you are able to calculate that how big this cylinder force should be so that it can lift the F what is in here. We still have here this F divided by 4, and we have here this, what's it called, B, which is equal to F divided by 4. And in here we have the cylinder force. And in here we have this middle joint. If we put it like this. And then of course you can split these in Y and X components, and like Nikolai told, this X component of this point and this point, they are simplifying each other, and it's the Y components that matter, and then you are able to calculate this torque, for example, over this point, taking account all the perpendicular forces what we have here, and you are finally able to find out what is the needed cylinder force C. Does it sound reasonable?
Absolutely.
Sorry, is that the Y of the cylinder force is also equal to the Y direction of middle joint support force?
It's not exactly like that because they are in different positions.
Okay.
But it might be. So there is a cylinder force X component, cylinder force Y component, and middle joint support force Y and Z. And this Y component of the cylinder force is the one that really does the work. But the cylinder force needs to be much bigger because most of the force that it creates is this X force. And now it's just a normal static problem. Okay, and you think that you're able to solve now this problem and to create a cylinder force, and it would be, I think, smart now to use this MATCAD and write all the formulas there, so that when I'm pretty sure that you need to do some iteration, you won't get the exactly correct results immediately, but you need to play a little bit and find out that what could be, depending on how big cylinder forces you get, you are able to calculate that what should be the correct diameter for the cylinder. And then at the same time, you need to find out such cylinder that the assembly length, so the minimum length is suitable, and it can create a stroke, a needed stroke in your system.
Excuse me, I have one question.
Yes, go on.
Like, there's the attachment point between the cylinder and the axis, which is near the end of the structure.
So you mean this point? This is a dimension that you can change. So in the report, you should show me this kind of picture, and where is visible that what kind of attachment points you have chosen. But this is something that you can freely select the suitable one.
Because now when I dimension it in vertical direction, it just show about 8 point something millimeters, which is really small for diameter of the cylinder.
Okay, so can you share the screen and show me?
Yes. So in here, when I dimension these things here, it's just 8 point something. So if the cylinder, we attach the cylinder here, so the cylinder might come to the solution that they will touching the ground with 8 point something.
Yeah, but in real life, I think this is a pivot points what we have drawn here, and in a real structure, this is not the level of ground, but it goes still a little bit more down there.
So how much is this going down?
I don't know, but I think you don't have to care about this. It can be as small as it is. It doesn't matter, because if we have a look at the picture, for example, in Moodle, we see that. Let me share the screen once again. If we have a look at this point here, we see now that the pivot points are in the middle, and there is still some material in both directions. So they are not just lines, but there is some structure that has some thicknesses and width and so on. Now in this SolidWorks sketch, we are only playing with these middle points and lines. So I think at the moment you don't have to care about that issue at all, because you are not going to design this lift in a mechanical point of view. Then if it would be a case that you would really do the mechanical design with SolidWorks, then when you would model and extrude all the parts what are needed, then you would see that how much room you would really need there. But now this is not the aim of our task in this design exercise. Now we only concentrate on this hydraulics and we are not going to design the mechanics.
And I choose the group A, so they state that the lifting range is 0.1 meters. So in the drawing, should we reduce the number?
So in your case, it would mean that your starting point is this.
So it is not like from the ground, but from the.
Yes, you can think that it is from this point. So the difference between these pivot points, difference between the joints is the thing what matters in this time. This is your starting point.
Yes, thank you.
Do you have any other questions in your mind at the moment?
I just curious how to calculate 100 dimension, because if we neglected the room dimension, so we just freely reach the number 100 to 0.
Yeah, you can do that if that is, if you feel it's the easiest way, then you can do that. No problem.
Yes, thank you.
And if we still have a look at this picture, we notice that actually it is very close to 0 here. The cylinder attachment point, it is not over here, but it's very close to this pivot line in this structure. And it is, in many cases, it is the most optimal place. But not only solution. So, like I told, you need to select a hydraulic cylinder, like all other components, and there are very many different companies that are manufacturing hydraulic cylinders. I'm now going to show you one. This is definitely not the only one, but I just use this as an example. And you need to have such a hydraulic cylinder that has these rotational joints in both ends. And this company has this kind of PDF that shows some information about this hydraulic cylinder. This information is, well, actually it is in Finnish, but there is only some things here. This K here, this iskun pituus, it means it's a stroke. That how much stroke we are able to get from this certain cylinder. And then this letter Z, it is the minimum length of the cylinder. So these are let's say the jet, and then the maximum length, which is the jet plus k, they are the things that should fit roughly here. So in the minimum position, this dimension, what is now this 521, should correlate to this set. As you can see here, it's the distance between the attachment point here and the attachment point here. This is the absolute minimum dimension that you can reach with certain cylinder. Is it clear?
Yep. And how do we get the maximum dimension?
And the maximum dimension, if we put here, for example, now this 1100. Now this dimension here, it is this jet plus the stroke. So the first line here, now the maximum dimension would be 339. So this is the free space inside the cylinder, what the piston can move. So the maximum dimension is K plus jet. And the other numbers here, you see this AL, this is the piston diameter, and this SP in this table means the rod diameter.
And AL is for cylinder diameter?
Yes, that's the piston diameter. Cylinder diameter, piston diameter is this, and the rod diameter is here.
And does ISCO stand for the stroke?
Stroke. Yes.
Yeah, okay.
You can see here there is the AL and there is the SP. And then K is here and Z is there. And most likely you will need a little bit bigger cylinder because the amount of force what you need is not so small, which means that this cylinder that I used as an example, this 25 millimeter diameter is not enough, but you will need something like 40 or 50. So it's this part of the table that you need to study. But like I told, this is just one example. You are free to use any cylinder you find in the internet. This was just something that I think was quite clear, the picture here, and quite clearly told these different things that has any effect.
Could you please leave the link for this website or PDF file on the Moodle? In Moodle.
Yes. Actually, it seems that they have an English page as well. But in the English page, they don't have this table. So it seems that they don't have so perfect English pages, but yes, this is the address. I will put it in a chat.
Thank you.
So the first step here is to calculate the cylinder force and find out such a cylinder that fulfills your need, both in a diameter and in a stroke and in an installation length. And like I told, it will be a little bit iteration. It might be that the first calculation round will not bring you the correct result, but you need to play a little bit about or with these dimensions here. And in a report, I would like to see this kind of sketch about the cylinder length in both positions, in fully down and fully up, and then the calculations, the free body diagram and the calculations, static calculations, that how much force you really need. And like I told, I suggest that you would use, for example, MATCAD to create those calculations so that you are able to easily change the starting values. All right. And then more about this problem.
Excuse me, one more question. So we just care fully about the pressure in the cylinder. Do we have to also consider the buckling of the cylinder?
Yeah. That was an excellent question. You have to care about buckling also, and I'm going to talk about the buckling later. But I think that these first calculations you can, of course, if you know how to deal with buckling, you can go on all already. But I think the first calculations, it's just the basic dimensioning of the cylinder. The buckling calculation is more about dimensioning the rod. I'm going to talk about buckling calculations, but that was not my intention to do it today, but later in this course.
Yes, thank you.
Isn't buckling already taken into account by the cylinder manufacturer, or we should calculate the
You have to confirm that it will be fulfilled. So you need to do some manual calculations because the cylinder loading situations can be a little bit different. So you can't think that the manufacturer has taken care of them.
Okay, I see.
Okay, let's do so that I will put here single acting cylinders. I'm going to show you what is the one problem here that you need to solve. So if we have an what? They are still double acting? I think they should, no, they are single acting, but they have this breather valve here. Okay, yeah. So we have this very simple system with 2 cylinders. And if we simulate this, they are moving up nicely. Okay, now we don't have any load, so they are not coming down. So let's put some load here. Let's put, for example, 0.5 kilonewtons. Same amount here. Let's make it visible. They are moving up the same speed, no problem. And now since we didn't have any kind of throttling, they came down too quickly, but still at the same stage. But what if we change something so that we will add here a little bit more load? Let's put here 1 kilonewton instead of 0.5. What do you think that what will happen now?
And the right cylinder come back faster. And
So which cylinder will move faster?
the one with the more load, where the one where more load is applied.
So you think that this will move faster?
I think one cylinder will come up first and the other cylinder come up later.
Yes, this is what is going to be happen. So the left cylinder, which has less load, this moves fully up at first, and the other one will start the movement after this has finished moving.
But how about coming back?
Well, coming back, I think they will come more or less at the same time, but if someone is faster, then it's this one, which has a bigger load. But let's put an pressure meter. I want to see bars. So they come back so quickly that you don't see the difference. But the point was that if we have some unbalance in our load, always the oil goes where it can go the easiest way, because this left cylinder needs less pressure than the right cylinder, and the pump generates only that amount of pressure what is needed here. So in the beginning, let me still change the options a bit so that we can see better what happens there. Let's slow down the simulation. So now the left one goes up with 26 bar, and when it reaches the end, then the next one starts the movement and it needs 51 bar. And imagine that this would be our car lifter. I think it would be a disaster that the left side would go first up and then the right side would start going up. So this is something that we can't accept. because in real life it might be that the car is not fully symmetric in a place, but a little bit more of the load is on other side. So this is a real problem. It doesn't have to be so big, the difference in load, even if in theory, if we would put here instead of 1 kilonewton, if we would put here 0.55, I think this would be enough. Still, this would be the case. So that's why you need to have some hydraulic solution for this. You need to find out what kind of hydraulic components you have to use so that you can prevent this happening.
Can I ask a question like, if the cylinder is not compression, they are like tension. So if they actuate up, and the force will become more instead of less. So the cylinder will come up at the same time, but not at the exactly at the same time, but like there's some small limit. Is that true?
No, I have to say that I didn't get fully what you mean.
Like, can you come back to the drawing models?
In SolidWorks?
Yes. And in here, like, if the cylinder, if the lifter going up, and the force in the cylinder will reduce, isn't it?
Yes, that's true.
So if we doing the way that opposite, that instead of cylinder in here is compression, we made it some kind of tension things, and if the lifter going up, so the cylinder will like become more force, isn't it?
Now I don't understand that. How would you put the cylinder so that there is no compression? I think in every case there is some compression in the cylinder. Even if you split it around, still there is compression.
If there is another models, is that possible? Like, I just asked about the other things, but not this relating to this more or less.
Mm. So I think it doesn't matter if you have any tension or compression. If you have a different load, then you have this problem.
I mean that.
If the load is fully the same, then they will move the same speed. And also in a normal, in many constructions, there is some mechanical connection between this part and this part. And if you have this mechanical connection, then you don't have this problem at all. I think this is the same case that I discussed with one of the groups in this project A.
Yes, and okay, thank you.
Is it possible to add this connection in Fluidsim?
What connection?
Well, mechanical connection between cylinders.
No. It's not possible. Or at least I don't know that it would be possible. I think it is not possible. All right. Basically, now this was the information that I wanted to talk about this design exercise. Do you feel that you have now enough information that you can start doing this and you can individually work next week? I think you don't need to concentrate so much in this hydraulic circuit yet. It's more important that you will calculate that what kind of, how big cylinder forces you need.
Well, you said that we should work individually, but isn't that a group assignment?
Yeah. I mean, in a group, individually in a group, meaning that I'm not going to have a lecture for you next week.
Oh, so we don't have a lecture next week?
Yeah, we don't have a lecture next week, but you will have an individual work going. You have to start working with this design exercise, and then week after that I will start guiding you more.
So the week after the next week, we're gonna have the lecture and like check our results and calculations, all this stuff.
Yes.
Okay, great.
All right. So everything is clear so far. What comes to this design exercise, or still any questions, or you know how to start?
Sorry.
Mm-hmm.
It seems that can you look through the group list? Yeah. It seems that I'm in my own group D1, so can I do it?
You can do it alone, but of course I think it would be better if you would do it together with someone else. How about Surai? Do you want to do it together with Tran?
Okay, I have no problem.
So I think you are manually able to leave one group and join to another group.
Okay, I'll go to the group D1 then.
Can I ask about the exam feedback?
Yes.
Because I'm interested in the essay type question. So just curious where I lost points, what could be done better, all this stuff. Or if I were wrong somewhere.
So now we have two options. I can show in general talk about this exam, or then I can split you in smaller groups and I can talk individually with you about your own results. So which way would be better?
Well, I'd prefer to do it individually because I have like an exact question about exact task in my exam.
Okay, so maybe we can do so that now I think I don't have time to go through all the exam with all of you, but if I split you in breakout rooms and I can go through with those people who I have time, and then during the next lecture, which is after 2 weeks, we can talk more about this exam in general level. Is that okay?
Yep.
Yeah, will there be any re-exam?
Yes, I think that there will be a re-exam at the end of April or in the beginning of May.
Oh, thank you so much, sir.
Okay, so I will now split you in breakout rooms, and if you don't have any questions regarding the exam, I think that you can leave now, because I'm not going to show anything else. So